So I'll give you an accelerated tour through tree search, but the slides have more detailed information. But it's really a pretty intuitive idea, so I think the accelerated tour will be fine. Yeah, so I'm gonna really just try to get through the ideas. So just like we saw this sort of diagram for Monte Carlo planning with policy improvement, and the only difference was at every state we were doing something different down here. We were using the simulator. For example, policy rollout, we were trying each action and then simulating a policy some number of times. Now what we're going to be doing is we're going to be using the simulator to build some sort of tree that sort of looks ahead at the possible futures that can occur. When we were doing policy rollout, the only possible futures we looked at were ones that could be generated by the policy that we were given. And that's why we just had these straight lines. And here, rather, we're going to be able to look at all the possible futures, we'll say, and search through them and try to find out what the best action is. So unlike policy rollout, which if you give it infinite time to run, at best it will converge to sort of the action that one iteration of policy iteration will give you. So it's not going to be optimal. This approach will actually converge to something that's optimal in some sense if you run it long enough. So that's one major difference here. But you can think of this very much like how you would build a chess engine, except now instead of having an opponent, an adversary, where you end up with a minimax tree, we have the environment as a sort of a non-adversarial opponent that just acts according to sort of a fixed distribution of outcomes. So we'll see how that works out. So let's just move on. So I'll say, there is a whole view of this stuff that is based on bandits, in particular recursive bandits. If you're interested in that, there's stuff at the end of the slide deck, but it's kind of a harder way to understand this. But it's actually more general in the sense that you can plug in different bandits at that point and you get different algorithms. But we won't be covering that here. So the key idea. So if we remember policy rollout. That was based on policy iteration, right? And we basically use the simulator to approximate a policy improvement operator, right? So policy improvement is just compute the Q function and take the action that maximizes the Q function. And we used the simulator to do that at a particular state, as opposed to policy iteration, which does that for all states. And yeah, so it was focused on a single state, and then we could do this for multiple stages and simulate multiple iterations of policy iteration, but the complexity sort of scales exponentially with the number of stages. So you're going to have to sit there and think longer, exponentially longer, the more iterations you want to simulate. Now, what we're doing today, sparse tree search, we're calling it, or Monte Carlo tree search, is instead based on finite horizon value iteration instead of policy iteration. And here we're going to use a simulator to approximate the Bellman backup operator, which turns out to be relatively straightforward. And we're going to focus on, if you remember, finite horizon value iteration, which we'll see in a moment, that basically computed values for all the states in the state space at every layer. We're going to focus on just computing the value for a particular state and the action for a particular state. So it's going to be more focused. And the complexity here, like the time that we have to think at each decision point, is going to scale exponentially in sort of the horizon that we care about. So let's see what that looks like. So this is just a reminder. So this is the Bellman backup operator. You remember this? This is from I guess you've implemented this. You've seen it a lot. But we just have some initial values. These might be 0. They might be some previous value function. And then we just basically compute the Q values for each of these actions. That's what this step is doing. And we take the max, right? That was the Bellman backup operator. So we've seen that many times. And then we turn that into an algorithm, finite horizon value iteration, where we would just start at V0. So this is sort of horizon 0 steps to go. You might initialize these to 0. Then we did Bellman backups for all these states to get the values with 1 step to go. And here we got the values with 3 steps to go, right? And you can keep on doing this as long as you wanted. And we know when we had a finite horizon, the best action can depend on the horizon that you're at, right? We talked about that many times. And then, of course, you can also, you get this best action by just looking at what action results in the max. Now, so tree search can basically be viewed as a focused version of this, right? So if we were to say, your robot is operating in the world, and this happens to be the current state, right? This highlighted state, and all we care about is computing the action that finite horizon value iteration would compute for that state, right? Let's just say that that's our task. Well, a lot of these states are not actually relevant to computing that value, right? So, for example, if you look at the places where this state could go, it's just these states up here. And where can this go? It's just these states up here, right? So there's a lot of what we'll call unreachable states. So there's a lot of parts of this whole graph that are unreachable from this current state. And so you don't actually need to touch them to compute the value for this current state, right? And so what does that look like? Well, that would look like this. And I'm only showing you one action here, but you can imagine that in general, there's just a fragment of this graph is going to be relevant to computing the value of any current state. So you can imagine this will give you a lot of savings, right? Because you don't have to expand nearly as much as you had to previously, where previously we were sort of just going over every state. But bottom-up dynamic programming can't really figure out what's relevant to the current state, right? Dynamic programming just kind of says, okay, I'm just going to do it for every state. I don't care if it's relevant or not. And so instead, if you're familiar with who's seen sort of the notion of recursive algorithm and memoization as sort of a way of doing, it's kind of equivalent to dynamic programming in some sense, right? So we're not going to cover it, but a lot of dynamic programming algorithms, you start off with some recursive equation that you're trying to compute, and you could compute that in a forward way, and dynamic programming can compute it in a backward way or some iterative way, usually. And the forward way here is actually going to be more convenient because we'll start here and then we'll just be able to just touch the states that we care about. And so we're essentially going to try to implement dynamic programming in a recursive way. And that will allow us to focus on the current state. And there's sort of different trade-offs there. All right, so that's all there is to it. You see, this is a graph. If you sort of flip this around, it's going to be you can think of it as a search graph where the current state is the root. Tree search often will be formulated in terms of trees, so they won't sort of merge these paths. So for example, at this level here, they would actually have two versions of this state, one coming from here and one coming from here. Turns out you can merge these things with no problem, but that's sort of a detail. We'll talk about that in a moment. So that's just to motivate what an expecting max tree search is doing. And so these are the recursive equations that I talked about. Right? The recursive equations are for V star, which is in terms of the Q function, right? And the Q function is again defined in terms of V star at h minus 1, with h minus 1 steps to go. Right? So we've all seen this in the past. And you could keep on expanding this, as we see here, in a recursive way. Right? And a recursive implementation of this would just literally just have recursive calls that bottom out when h is equal to 0. Right? So that you could all implement that in a few lines of code, more or less. Right? Just these are your definitions. You write a recursive algorithm that computes this, and bam, you're done. Right? And the thing is, it will take a very long time to run. Right? And so what that would look like, though, if you were to expand it, would be something like this. So you get, it basically is expanding an expecting-max tree. So as opposed to a minimax tree where min sort of corresponds to an adversary that's trying to minimize your performance, expecting-max means that nature is sort of taking its moves from a fixed distribution, so it's giving you some expected performance. So the expected max tree is just implementing that recursive formula. So this root is going to be focused on state S. We want to compute the value for H, capital H, or horizon steps to go. You would look at all the actions here, and you're going to max over those. And those lead to expectation nodes, which sort of will look over all the states that can result from those actions. They'll be weighted by the probability of reaching each state, and then you'll do a max at those states. So this is just the expecting max tree. Now here, the number of leaves and roughly internal nodes is going to be k, number of actions, times the number of states to the h power. Right? That's just the size of this tree. The branching factor is k times the number of states. And so that's scaling with the number of states, which is bad because we're thinking about situations where the state space is enormous, and so we wouldn't even be able to implement this for one level of the tree. So all that these Monte Carlo algorithms do is they instead of enumerating all states, they'll sample states. And so if you think of like this, this combination of max and expectation, this combination of layers, if you think of that as a Bellman backup, we're just going to be approximating a Bellman backup by sampling some number of these states from the right distribution, and instead of just expanding all of them. Right? So that's all we're going to do. And so we're going to define something called the sampling width. Instead of expanding all the states, when we're here, we're in state S, and we're considering action A, we're just going to sample from the transition distribution W states. And that's going to give us sort of a tree that has K times W to the H number of leaves and also sort of internal nodes. All right? So is that relatively clear? Any questions about this? Right? So it's doing nothing more than implementing the recursive equation, and the expectation in that recursive equation is done via sampling. You approximate via sampling. All right? Okay. Yeah, this is just showing you sort of maybe a clearer picture of how things work. So we have a state, action, and then each of these actions we're sampling W next states, right? And then each of these states, you consider their actions, and then you sample W next states. And as I said before, usually these algorithms are described as tree search algorithms, right? Because you'll notice here where every time we sample a state, we're creating a new state here. But it could be the case that this state that you sample here is the same as this state that you sample here, right? You can have repeated states at a level. And in practice, usually implementations are going to merge those across levels. It's very easy to implement. You just keep track of what states are here. You keep a dictionary, and when you generate a state you already have, you put a pointer to it. and that the theory and everything it's not affected by doing that. So I'll mention a theoretical result later on. You can do that merging, and it's almost always good to do. Otherwise, you're just building a bigger tree than you need to. And effectively, so if this was the same state as this, you can think of it as if you build a tree, you're doing repeated work, right? Because here you're going to have to get a value. I don't know why this pointer goes away. You have to get a value for this tree by expanding a subtree underneath it. And here you're getting a value for this state by expanding a subtree. Well, you might as well just do that once and just share the workload. Okay? So that's why that first value iteration view that I showed you, that was sort of a graph, but they usually define this as a tree. But implementations usually use graphs, right? So any questions about this? All right. So one thing that you may notice is that this could have a high memory cost if you literally built this tree and then computed the value going up. Do you actually have to build this full tree and store it in memory? Do you think? No. Yeah. How could we avoid that?
You can basically go down a single path, then as you go up to compute other parts of the tree, delete the parts that you have just gone to.
Right. So for example, we would just say, okay, from this state, we're going to first take A1, and then we're going to focus on computing this Q value for A1. We sample this state's value, and then we'll consider A1 here, and then this might be the bottom of the tree. We'll propagate that value up. Now we don't need this anymore. Then here we'll sample this. We'll propagate that value up, and we don't need any of this anymore. After we've sampled all those, we've got the average values that we developed. Now we can propagate this value up, and we don't need this anymore. So you can do a depth first expansion where you don't have to actually store the values, because once you're done with a subtree, you don't need to store it. You have the value that you needed to compute from it. Okay? So long story short, that's what this code does, and we're not going to go through it. It's just a straightforward recursive implementation. Okay? But the memory cost is basically just linear in the horizon. That's all. So that's pretty. That's nice. All right. So this algorithm, this pretty simple algorithm, is called sparse sampling, and it was, I guess the claim to fame was it was the first algorithm for MDPs that could compute near optimal actions in time that was independent of the size of the state space, right? And the way they're able to get away with that is this W. What they did is they analyzed. So you can use a lot of basically, if you apply the Chernoff bound recursively, working up this tree, you can figure out how big does W, this sampling width, need to be so that you guarantee that the values you get here at the root are close to the optimal values. And so it's just a mathematical analysis of that process, bottom up, how the errors add up as you go up the tree. They did that. And the sampling width and the value of H that you need are independent of the size of the state space. So you kind of get a pat guarantee on optimal policies that is independent of the size of the state space. And so that was the claim to fame. So that's the good news. But the bad news is you don't ever want to use the theoretical values of W and H, just like you never really use the theoretical values of anything. So because they're just way too large, and you might as well expand the size of the state space. So if you're going to use those values. So in practice, these are sort of hyperparameters. H and W are just parameters that you pick, and the complexity scales pretty quickly with both of those. So you try to find the smallest ones that are going to be effective for your problem. And the other thing that you can do, and this is really the way that these are usually going to be used, this straightforward tree search. The other thing you can do is if you've learned an approximate value function, for example, using TD learning, for example. Let's say you used reinforcement learning to learn an approximate value function. Well, then if you do have this simulator, you can do a little bit of search. So maybe you expand the tree 2 levels, and you apply the value function at the leaf. And if this value function is reasonably good, often the action that you take up here you'll do even better than if you just greedily followed the value function. Okay, so it's not uncommon to sort of have an approximate value function at the leaves, and then you do a little bit of search, and that can really improve things quite a bit. If you were just to do one level here of search, and you apply the approximate value functions here, it's kind of like you're just doing a one-step greedy look ahead, which we've talked about many times, right? If I give you a value function, you can't take an action unless you do look ahead somehow. And so this is just saying, well, you could do multiple steps of look ahead, and you pay the price of an exponential price in terms of the number of look aheads that you do. All right, so that's sort of the practical way that you would likely come across using these. And this is very analogous to what chess engines do, right? Chess engines expand a tree and apply an evaluation function at the leaves. All right. So there is some bad properties of this basic type of algorithm, and basically, I like to say that they have bad anytime behavior in the sense that you almost can't take it. You really don't get enough information to take an action until you've almost completed the search of the entire tree, right? So for example, you'll do the search to completely expand this subtree, and you get a value for this action. And that's almost like half the work that you have to do, right? It's half of the exponential time. Then here, you have to do the same thing for this action, and you can't choose between those actions till it's all done, right? Till all of this work is done. And so if you have a non-trivial depth, there can be you spend a lot of time before you can even get any information to select an action. And for that reason, we say that this is not really a good anytime algorithm in the sense that when we want anytime behavior, generally what you're thinking of is you want an algorithm that you give it a little bit more time and it gets a little bit better, right? And you don't have to give it like a huge amount of time to get any performance at all. And sparse sampling is kind of like that. You have to give it a huge amount of time to just get a result at all, as opposed to there's no way to like say, okay, I just want to give you 10 more seconds and let's see how much better you can do. It's like, no, I'm going to need like 3 hours to see how much better I can do. So what we'd like to do now is get an algorithm that has a little more, some better anytime properties. And what this is going to have to do is going to have to do, smaller. It's going to have some sort of smaller operation each iteration that gives us values at the root that we can use to select actions, as opposed to having to completely go through an entire subtree. All right, so this is where the idea of Monte Carlo tree search comes in. And I'm going to give you I've got a lot of slides for this, but I'm going to give you a quick tour that sort of gives you the basic idea. There's really not too much to it. But it became really popular when this paper came out that introduced this UCT algorithm. So UCB is upper confidence bound. You've seen that for bandits. UCT was basically an attempt to apply UCB in a tree search setting, so upper confidence tree. And it started with this theoretical questions. Can you apply it to tree search and sort of get these pack guarantees for trees? and they were successful there. But the framework, Monte Carlo tree search, has been around a lot longer than that. It sort of came out of the Go playing community, um, and it's sort of known for having good anytime behavior. So it does little bits of work that give you useful information each time. Um, so yeah, this picture is basically saying that uh, some level, Monte Carlo tree search came out of this idea that for Go, they originally found that they had a really hard time coming up with good evaluation functions for Go boards. Like in chess, you can come up with evaluation functions by looking at the pieces. So there are different pieces, and they have different values, and you can even just look at the relative weights of the pieces that are on the board to get some evaluation function of a board position. And then they have other properties that chess masters came up with. In Go, they had a much harder time coming up with good evaluation functions. People worked for years and years on Go programs, and they were not very successful. And then it turned out that one of the more useful or effective evaluation functions, right, this is just give it a board and if you want to give it an estimate of how good it is, was to just play random games. So you take two monkeys that don't know how to play and you play random games, many random games, and whichever monkey wins more, you say that side has the advantage. Yes.
Did they find that this heuristic worked for other games, or was it domain specific?
This was for Go, and obviously rolling out random games is not going to be useful in, well, I don't know most, but a huge number of other games. So chess, I would not expect it to be useful at all because most random games won't end up in a checkmate in any reasonable amount of time. Go is nice because the board just fills up and you can't sort of go on forever in some sense. Chess, you could just kind of move pieces all over the board, just uselessly over and over and over. So you would need to have a little more guidance at least. But these random rollouts, like I was saying for the policy rollout algorithm, you'll often find that starting with a random policy, you'll get a big improvement. And Go, this was one of those cases. So when they noticed that, they sort of said, well, that's great. You could use it to just greedily select a move by I'm going to consider all the moves and then I'm going to evaluate the board positions that emerge and I'll take the best one. But then they expanded that idea to what's called Monte Carlo tree search, where they're going to start building a tree and evaluating leaves by these random rollouts. So the picture of Monte Carlo tree search sort of looks like this. This is a standard picture. So Monte Carlo tree search, unlike sparse sampling, you actually store the tree in memory. And the reason you do that is because the tree in memory is storing some statistics that tell you where you want to expand it next, as opposed to sparse sampling, which just doesn't need to store the tree because it doesn't do any sort of selective expansion. It just expands everything. So when you're running Monte Carlo tree search, at any point you have sort of a current tree that you've explored. And you start off with just a single node, the state that you're at. And what it will do, it will use something called a tree policy. And that's, different Monte Carlo tree search algorithms have different tree policies. It will use a tree policy that sort of starts at the root and then takes some path in the tree to a leaf node. Okay? And so intuitively, you might want to take paths that tend to go to more promising parts of the tree, but don't ignore other parts. So they also explore parts that aren't as promising, but maybe have a little bias towards the more promising parts. So you first run your tree policy until you hit a leaf. Then you'll expand, and this could be just you take a random action, for example. So you expand the action. And then from that new state you end up in, you run the default policy, which the traditional default policy is just a random policy, the random rollout. And that's what this is showing. And that gives you some valuation, a value estimate of this state. And then you will back propagate that information through the path that you took down to this leaf. And so if this looked like it was a good leaf, like the valuation said, well, you're going to win the game 100% of the time, then this propagation is going to sort of make the statistics of these nodes on this path look better. And so, and then the way that the tree policy will typically work, it's going to take that information into account and sort of bias itself towards the better looking parts of the tree. Okay, so every iteration, you're adding a little bit of information to the tree, and in particular, information along one path of the tree, based on whatever evaluation you get from this run of a default policy. Okay, and obviously you could also use non-random default policies if you wanted to. Another approach that's also used is if you have an evaluation function that you've learned or you just have, you could just use that here instead of running a policy to get a value. So any of those approaches can work and have been used in all kinds of combinations. So any question about this basic structure? Right? So when you hear Monte Carlo tree search, this is all it's doing. Right? Very easy to build. Every iteration adds one node to the tree and sort of updates information along the path that was taken. Okay, so that's Monte Carlo tree search. Not too much to explain there. And compared to something like sparse sampling, which kind of builds a uniform tree, like it's just uniformly expanding, Monte Carlo tree search trees will sort of have non-uniform growth, where usually they're going to be more heavily biased towards areas that look more promising. They'll sort of go more deep. They'll go deeper into more promising areas to discover whether they are actually promising or maybe they were looking promising but they're really not, and then they'll have to go expand somewhere else. Right? So the thing we haven't really said is, well, what is that tree policy, right? What policy do you use to select a leaf? And then the default policy, that could be anything. It could be random. So, yeah, this is sort of the generic MCTS. I think we've kind of shown this. So I'm going to show you what UCT does. So this UCT algorithm, as you might guess, the tree policy is something like UCB. So at every node in the tree, we're going to store, so every node in the tree corresponds to a state. And we're going to store sort of the average values of trajectories that went through this state action pair, right? So every trajectory sort of goes through some set of state action pairs in the tree. And at every node, we're going to store these Q values, the counts, the number of times you took an action in a particular state, and the total number of times you visited a state during the tree search, right? So this is the information, and this is basically the same information if you thought of S as defining a bandit problem, right? If you remember the UCB algorithm, all it kept track of is how many times have you pulled the arm of a bandit, and how many times have you pulled each arm in your bandit problem? How many total pulls have you had? And what's the average sort of value you've seen for each arm so far? And that's equivalent to these things. It's just now we're indexing by the state because you're going to have one of these at every single node in the tree. And so the tree policy for UCT at a particular node is just going to implement this. So we have the Q value, which action looks best. So that's sort of the exploitation term. And then we have this exploration term, which we've talked about when we talked about UCB. Remember, the more times. So if you stop taking action A in this state, what happens? Well, NS will just increase. It'll keep increasing, whereas the denominator does not change. And eventually this term is going to get big and you'll have to take A because it will be the maximum action here. So that's your exploration term. And theoretically, what this paper showed was if you have to add a C here, like this constant, to the exploration term to make UCT sort of work. And the reason, okay, so let's just think about the reason is that if you think of these as, if you think of there being a bandit problem at the root here, traditionally in multi-arm bandits, the bandits, like each arm has a fixed distribution, right? So you have each arm, we said, has a fixed distribution over rewards, and that's just the same. It's the same throughout all time. Here, really the bandit problem, if we want to think of it as a bandit problem, at this node for selecting A1 versus A2, it's a non-stationary bandit problem because the reward that you get when you pull this arm depends on what happens in this tree. And this tree is always being changed and updated. And in particular, it's usually going to improve. Like the reward you get is going to tend to improve over time. And so these are non-stationary bandit problems. And because of that, the analysis basically has to throw in this C so that you basically have to explore more. And basically what happens is things sort of converge from the bottom up. Like eventually the bandits near the leaves will converge because leaves are sort of stationary bandit problems and you just converge from the bottom up. The unfortunate thing is this C has to be really large in theory. It has to be equal to the horizon. And if you use that, basically you're, for any practical time frame in any reasonable horizon, you're just going to be exploring all the time. So in practice, UCT treats C as a hyperparameter, and you just tune it for your particular problem. But what you'll find is if you're trying to make an algorithm that works in a very general way, so you can give it different types of problems, and you want this one algorithm to sort of work, it makes it difficult because you always have this hyperparameter that you have to tune somehow, and that's just an extra knob that's really annoying. So I tend not to use UCT in my research because it's a really hard thing to predict what it's going to do. If you have a fixed problem and that's all you care about, yeah, you can tune the heck out of it and you might be able to get it to work. But it's a pretty common algorithm, and I'd say more commonly people use some variation and they'll call it UCT-like. So if you look at what DeepMind did with AlphaGo, if you look at the details of how they do their tree policy, it's UCT-like, but it has other terms in it, and it's pretty much a heuristically motivated thing that they came up with. So anyway, this is what UCT would look like. So let's say this is the current tree, and we want to run one iteration. So it's going to form this bandit problem, and this is just showing this is the average reward we've seen so far at this node. And this is the number of times we've pulled this arm, and the same here. We pulled this arm once. So most likely, UCT, the UCB rule, is going to pick this arm here, we'll say. And so it does, and we go down here. And now we have a new bandit problem, and these are the statistics here. We go down here. Now we hit a leaf, right? So you can see this path was just completely greedy this time. We hit a leaf, we expand with our default policy, and we ended up with a 0 value. Now we'll have to put this up, and we change our values. So everything along this path got a little bit worse because previously they had greater than 0 values, and now they saw a 0 value, and so they're a little bit worse. Now you define a new bandit problem for the next iteration. Now maybe it goes over here, and you just keep on doing this over and over and over till you run out of time, basically. So it's an anytime algorithm, creates one node every iteration, and you just build as big of a tree as you can in the time you have. And that's how this works. Any questions about UCT? Right, it's actually pretty simple after you understand what Monte Carlo tree search is and what bandits are. It's just putting those two things together. All right. So with the time remaining, I think I'd like to give you a quick tour of AlphaGo, and this is going to be a quick tour. I have a whole lecture on this, but basically, this is just showing AI solved the challenge problem of chess a long time ago. Now, any laptop, maybe even cell phone, can beat the world champion in chess. We've got algorithms that can do that, basically by brute force, alpha beta search with a evaluation function. We've another challenge problem was Jeopardy. We solved that, and the most recent challenge problem that was solved, you could say, was Go. So it took a long time to get there, though. Basically, at by 2005, it was still sort of considered to be an impossible problem for AI. Like there was no progress whatsoever, and basically the same types of techniques that work for chess did not work for Go at all. And I won't go through this, but one thing is Go is just a much larger game. There's many more moves. There's many more states, and you need to search much more deeply to do well. And also, as I mentioned, people that did not have good luck trying to come up with hand-coded evaluation functions or even learned evaluation functions for Go. And that might be partly because it's such a visual game and all the pieces are the same. So you take this position here, and it could be that if you remove this black piece, it's a completely different evaluation. And that's just a very hard thing to figure out. So people tried for 20, 30 years, but failed. And then we started making some progress once this Monte Carlo tree search idea came about, I was at a workshop around this time, and people who had studied Go for a long time were really annoyed by all this because they had worked hard on fancy heuristics and all that, and then these monkey heuristics came out, and it was beating them. It was beating the pants off them basically. And so there was a lot of progress, and then DeepMind, they had this AlphaGo system, which we'll talk about in a moment, beat the European champion in 2015. That was pretty exciting, but still people were like, the European champion is not nearly as good as the world champion. Go is mostly an Asian game, and usually players from China or Korea are going to be the world champions because they basically train a lot. They train a lot more people than we do. It's embedded in the culture. But then they had a showdown with Lee Sedol, and they beat Lee Sedol 4-1. Which Lee Sedol is sort of the Roger Federer of Go. He's been top of the game for a long, long time. Top 1 to 3 in the world. I don't know if he's still playing, but at that time he was sort of considered to be a god of Go. So that was a pretty big deal. And then after that, they beat the Chinese world champion, and that pretty much just settled it. Okay, Go's now ruled by computers in terms of the ability to win. And now people are doing a lot of analysis of the games that AlphaGo plays, and they're defining some new Go theory, like some of the old theory might not be quite right. So it's kind of interesting. You're in that stage of Go now. So they've made more progress since then. I will give you a little bit of insight into how this works. I'll put these slides up as well. But basically, what they did is they learned neural networks to do two things. One is to learn value functions for these positions. Because if you think of a Go board as an image, right, it's just an image with 3 values for the pixels, black, white, or empty. And around that time, lots of progress was being made in terms of deep learning, deep networks, doing really well on image recognition. So they're like, oh, maybe you could evaluate a Go board with a deep network. And that was just a conjecture. Who knows? It seems like a very different problem than recognizing a cat. But it turned out that with these deep networks, you were able to do it. And the deep network looked something like this. I've got a link to the Nature paper on this stuff, but the Go board comes in as input, and the output is sort of a probability of each move leading to a win. And usually this looks like it's a pretty sparse probability map, and they'll use this in two ways. They'll use it to basically, I'll show you this picture here. They'll use it to prune actions essentially in the tree. They don't explicitly prune, but low probability actions just are not going to get expanded. They have a formula kind of like UCT that has this probability embedded in it, and if the probability is very small, they're basically not going to expand it. So think of the neural network as one of the major functions is pruning actions from this tree, dramatically pruning actions from the tree. And the other function is they will either use the network to evaluate, so that they can learn a value function of this policy to evaluate leaf nodes, or they use rollouts of a neural network to get values for those leaf nodes. And basically, that's AlphaGo. The question is, how did they train the networks? They actually used self-play super reinforcement learning, but if you just tried to do reinforcement learning with two neural networks, self-play to learn Go, it's not going to get anywhere because it's too hard of a game to sort of get off the ground and start doing non-trivial things. And so what they did is they bootstrapped with 30 million expert moves. These are just games they've collected from the internet of experts, and use supervised learning to try to train a network that, given a Go board, produces the move of the expert. And they got 57% accuracy, which may not seem good, but it's actually really good because there's a lot of moves in each position. And who knows, these experts aren't even really following a consistent strategy with one another. So that was pretty remarkable. And this is actually a pretty good player, but then they used that as an initialization for self-play. And we've talked about this for TD Gammon. Remember that? So they did this, and the result of that was they got an 80% win rate against the supervised deep network. And the really, really interesting thing is just using the network to make moves, they were winning 85% of the time against the best tree search method. So just using this single circuit, just bam, here's a board and compute the move almost instantly, was beating the best tree search method at the time, which is going to expand this tree and do lots of thinking. So that was pretty impressive. And then you go and you insert that network into the tree in the way that we talked about, and you get AlphaGo. Well, this is the tree search policy that they use, just for anyone who's interested. So they take the Q value, so that's sort of the exploitation, and this is the probability for the action that the network gives, right? So in the beginning, all the actions sort of have zero Q value, and what happens is the network is really only going to consider moves that have reasonable probabilities, because everything else will just be tiny compared to those. So this is where the neural network goes in that tree search formulation. And this is how the pruning actually works. There's no real theory behind this. It's just something that it's just an intuitive thing. And then you have to tune C, and they use tons of computers to just run hyperparameter search on C for every single instance that they get. So finally, so AlphaZero, you may have heard of this. And this is the program that can learn Go, and they also showed it can learn to play chess like at the world class level in 2 hours. This is 2 hours of wall clock time, but real time, it's CPU time. It's a huge amount, and GPU time. And they also learned to play Shogai, which is like a Chinese version of chess, using AlphaZero. And this is a little bit different. It's actually simpler than AlphaGo. And the basic idea is just based on policy improvement. So AlphaGo, they train the networks with reinforcement learning by just having the networks make moves themselves, right? And here, what they're going to do is they're going to sort of insert the networks into search right off the bat, and just do self-play where they have their current network and they have their search, and the search can basically improve on the policy of the current network, right? So you do enough search and you'll get better actions than what the network would give you. And so they'll play games with this search, and they'll generate essentially supervised training data of actions that the search took and values that the search computed, and they'll update their networks based on that data. So you get an improved network, and then you apply more search, and you get an improved, you improve the policy even more. So it's kind of like policy iteration. You've got your improved network, you use that plus some search to generate improved actions and improved values. Use that to train your network, and you just keep on doing this. And if you keep on doing that, you end up with a world-class player. And so that was pretty interesting. You can learn to play Go, chess, Shogai, just with self-play, and a properly configured neural network and search. But this takes tons of CPU time. Like most likely, we wouldn't be able to do this here. You really have to have huge resources to do lots of this stuff in parallel. Because you can do the tree search in parallel, and you can have lots of games going on in parallel to learn. So it's really a distributed. You've got to use distributed stuff to make this work. So that's all I have for this. You got the slides if you want to look at more, and there's pointers to papers. But so this is pretty interesting stuff. And I think from this class, you've basically got all the knowledge you need to understand these papers, and you can go off and read your own now. All right, so we'll see you on Friday, and we'll come early so you can get ready for the quiz.